In this video, we'll start our discussion of linear algebra by talking about vectors. So linear algebra is mostly centered around this idea of matrices, but to get to that point, we have to start talking about vectors. So at the outset, linear algebra gives us a systematic approach towards solving systems of equations. There's a lot of things you can do besides that, and there's a lot of more mathematically interesting things that happen outside of just solving equations, but what we'll focus on here is mostly on this idea of solving systems of equations. So this might look something like this here. This is a nice linear system of equations for x, y, and z. I have three equations, three variables. That's a good thing to see. And we want to figure out what the solution is here, right? We have ways to solve this, and we'll discuss what we can do with that later. But the point is, a solution here is values of x, y, and z that solve simultaneously all three equations. Now we can think of these as three separate numbers. That's one way I think about it. But the way I want to think about it here is it's a single object that contains three values. So in terms of sort of normal coordinate geometry, we could think of this as a point in 3 dimensions that satisfies the system. Or we'll see in a second, the idea of a vector is exactly that. It's putting all of these things together in sort of one object that as a single object can solve this sort of system of equations. Here's our terminology that we need. We have a vector, and at its base, a vector is just an n tuple of numbers. It's a collection of numbers that are grouped together. In some ways, this is both similar and different from just sort of a point in the plane in 2D or in 3 space in 3D. But why not think of this for any number of components? So I could have 10 different components here and have a 10 tuple where I've got 10 numbers all listed out. And that is a vector. It is a 10-dimensional vector because it has 10 components to it. So the components of a vector are the individual parts of it. In terms of the geometry of this, it's generally thought of as an arrow to a point in space. So if I take the vector 1, 3 in 2 dimensions, you could think about this as the arrow going from the origin to the point 1, 3, like that. Same thing goes for 3D. Beyond that, you can't really draw pictures, but the idea is still the same. In terms of writing vectors, for reasons of how things work with matrices and what we'll do in linear algebra, we'll write these as column vectors. What that means is that instead of writing 1, 3 like this over here, we'll write it as a column 1, 3, where the 1 in the first spot means the x-coordinate and 3 means the y-coordinate. And similarly for other vectors, right? I could write a 4 vector or a 4-dimensional vector, 1, 3, 0, 2, in that sort of form like that. There's no real difference between how we write them, but this notation will be convenient for what we need to do later on with vectors. So we have these vectors. What can we do with them? Well, there's two main operations we can perform. If they have the same number of components, we can add vectors. In terms of geometry, this is just tip-to-tail addition of vectors. It's just putting the arrows together. Right, so if I want to add geometrically 1, 2 to the vector 2, 1, for instance, I can do that by just taking the vector from here and going out to 1, 2, then starting here, do the 2, 1 vector, so that's 2 in the x and 1 in the y, should give me there, and the resultant, or the sum, is this vector here, which we see is 3, 3 on the picture. We can also get that just algebraically, because when you add vectors, you just add components. This is the vector 1 plus 2 on the top, because I'm adding the top 2 components, and 2 plus 1 on the bottom, adding the bottom 2 components, gets me the vector 3, 3, which is the same as what I see in the picture down here. Now this only works if they have the same components. Right, if I have the vector 1, 2 that I want to add to the vector 3, 4, minus 1, that doesn't make any sense. I can't add those two vectors, they don't have the same number of components. It's just not a defined operation to combine these two things together. Right, a 2-dimensional vector plus a 3-dimensional vector doesn't really make any sense. The other thing we can do is multiply vectors by scalars. In terms of geometry, this just lengthens the vector or flips it around if the sign's negative. Take my vector 1, 2 again. It is this vector right here. I can multiply it by 2, and that just extends it twice as far in the same direction. Multiply this by a negative number, say negative 1 times 1, 2, that's going to flip it around to go back this way, the same amount that the first vector went originally. How can this work algebraically? Well, I can just put the scalar into each component, and that will give me the exact same result that I want. This should be the vector 2, 4, because I've multiplied each component by 2, which it is on the picture. And this should be minus 1, minus 2, which is also what I see from the picture. So multiplying by scalars, I can put the scalar, the real number that sits out front, into each component. That works out great. And for adding, as long as it's the same components, I can add them as well. The one thing we can't do is multiply vectors. So you may have seen the dot product previously, right? It takes in two vectors, and I can sort of multiply them in some sense, but I get a number out of this. I don't get another vector, so it's not really a multiplication on vectors, because it doesn't take two vectors and give me another vector back. There is not a multiplication defined on vectors. Something else that comes up in Calc 3 and other classes a lot is the cross product. Right, that took in two vectors and gave us a vector. But the problem is cross product actually only works in dimension 3. The cross product is sort of an application of a much more involved topic, but it only gives us a vector back if we're in dimension 3. So because we're looking at things that are not only dimension 3 here, we're not going to consider this as an option for things we're going to look at with linear algebra. So all things we really have for vectors are, we can add them, we can multiply them by constants, so we can do linear combinations of vectors, but those are the only operations we actually perform on vectors. So that's the instruction to vectors, what they are, this idea of just a couple of numbers or a set of numbers all in a vertical vector like that. And then what we can do with them, we can add, we can multiply by numbers, and build this structure around these vectors that will be super useful when we go into what matrices are, what we can do with them as well, and how they interact with vectors going forward.